Hello everyone, this is the third class of the course on nonlinear polymer rheology based on the book published by Wiley. Here are the topics discussed in this lecture.
You can go back to it if you need. So we will, as I said, we will try to introduce a few necessary pieces of information before we could move on. And they are sort of all scattered in the first two chapters, so it's not, it's quite easy for you to find where they are. So I will, so we are still in the introduction. Get it right? Introduction. We talked about a little bit about what is rheology. We talked about a little bit about Weissenberg number, right? Last time, concept of or definition of rheology. We talked a little bit using the example. I use that to, oh gosh. I use that to explain to you the need to pay attention to how fast we are deforming. So we had this defined, which is also equation no, this is all discussed in equation 1 point. In equation 1.3, for example. Okay, so the part I want to cover are a few things. So I explained to you before that that look like this molecule, the next moment move to here, will take a time of tau. And before anyone knows our polymer is made of this, there are some general ways to speak about this internal, if you like, this internal time scale. When I say internal, meaning in our case, we're dealing with molecules, so it's molecular relaxation time. The way to really understand this, understand what? Let me call my student who can turn this off for me or something. I don't understand this. Why it's a Hey, Travis, can you come to the lecture hall? I don't know, somebody turned on the smart board again. Yeah, mess me up, if you still remember how to do it. Yeah. Okay, okay, thank you. So this notion that any material has a relaxation time associated with it, any viscoelastic material. And if you recall last time, I told you when you speak about viscoelastic material, the fact you have elasticity is because you have structure. And when you have structure being viscoelastic, it means that structure has a finite lifetime. It doesn't stay there forever in that state. So there is some concept about how often things change. For example, the chain moves from the place in the black to the place in the red. This notion that there is some structure, it doesn't have to be our polymer structure, so it can be anything that is viscoelastic. And therefore, one needs to have a very generic way to speak about it. And this is something, of course, Maxwell, so I'm just talk about very briefly for you. Of course, this is what Maxwell long ago figured out how to think about it. He think about the simplest way to model a viscoelastic material. In fact, it's a linear viscoelastic material, is to think about having a layer of solid on top of a layer of liquid. Okay, so I think this thing is on, right? It looks like.
It should be.
There's an icon there.
It says it's on.
Huh?
It says it's on.
So it turned off.
Okay.
I see. So that's the place to do it.
Mm-hmm.
Okay. Now you should not mess up with me, right? Yeah. No, yeah. Thanks so much. Yeah. Now it should be just. Thank you. Yeah. And, but this thing's still here. That's okay.
Yeah, that's just there.
Huh? The student can see that too. Yeah. Okay. You will not mess up me. Hopefully, right? Yeah. Thank you. Thank you very much. Very easy. Very trivial to fix. The way to think about well, Maxwell model. I'm sure you too have it in your anyone else knows about Maxwell model? So I will be very quick, but basically it's in standard textbook it basically expressed as a spring attached to a dash bar. Basically, spring has a elastic constant modulus, and dash bar has viscosity. So I will not go into details, but rather than telling you that when you consider a combination like so, when you try to examine such an abstract construct, meaning obviously your polymer is not. I failed to take a piece of what I normally my favorite piece of PDMS, which is an uncross-linked melt. It has a TG of minus 100 C, so it's at room temperature. It's a liquid, and that piece of melt is just like a silly putty. It can bounce. It retains its shape for a little bit because its tau has a finite tau. And that piece of polydimethyl siloxane, of course, is not a sample made of a solid and a liquid. So this representing viscoelastic material as a piece of solid is just an abstract construct. But if you treat this construct, this duality that your material is both viscous and elastic, then you can find out the equation governing it, which is the stress, and how stress changes with time, is of a form very close to that of Newton. So this is Newton's law I mentioned to you before. And if you look at this one, actually this is the Hooking's law. The Hooking's law basically says that if you have a certain deformation, then, for example, you tilt it a little bit, then this tilt is x over h, gamma, of course, is x over h. Then it turns out the stress will be proportional to how much this tilt occurred or how much the shape change occurred. And these two limits are obviously quite innocent because they are linear. This is linearity comes from the fact they are linearly proportional to each other, okay? So why I say that? Because when you differentiate this, that's why I say this term is that, is the differentiation of the Hooke's law. So I hope that that's something you heard about. You know, Hooke's law, you should have heard about it. Newton's law, you should have heard about it. And this equation, obviously missing something. What's missing is whatever in front of this derivative, there should be a constant. Because the dimension, the units in an equation must be the same everywhere, okay? This has the unit of stress. This has the unit of stress divided by time, so there must be another time there. For the equation to hold, every term on every part of the equation must have the same dimension, same units. It turns out this tau, if you work it out, in fact, I had this Maxwell model recorded that it was uploaded to the website, to the Brightspace actually, just for your purpose. That has a little more details, but this is good enough. And it turns out this tau is nothing but eta divided by E, viscosity divided by modulus. So magically, this master, Maxwell, played a piece of magic by considering two elements, being solid and liquid. He come up with this treatment where a time scale just arises naturally. It arises telling you it is related to the viscosity of your material and the modulus, which is a sense of stiffness, a solid state property of it. And it's the ratio of the two. Okay? Of course, if you examine you cannot escape from it because you know from here that the modulus has the dimension of stress, okay? And viscosity has the dimension, look, viscosity is here, has the dimension of stress times time. Okay, so that ratio, of course, will give you a time. Okay? So all this is of course, quite elementary. All of a sudden, we recognize if you have a viscally elastic material, you should at least come up with some kind of relaxation time to characterize it. Any question? Okay, we move on then. So last time I talked about what we need to deal with is object that's made of, in the limit there are no solvent. You can have solvent, but then it would be less clouded. But basically, it's a dense melt. It has the mass density close to that of water, which is 1 gram per cc, right? Cubic centimeter, roughly. All of our organic polymers are of that, has that feature. It's lightweight, and then that's why our polymer is very useful because its specific strength is very high compared to steel, which is 7.8. You are much lighter, but you can be still strong enough, as light as that of water. That's our polymer. Of course, typically it's slightly less than 1. But there are polymer in the semi-crystalline state that will be larger than 1. Okay. So with that, let me say a little bit more about how we should think about our polymers. And there, I want to introduce you. So, of course, this, if you like, just trying to point out, if you like, what we doesn't listen to my finger. What we talk about Maxwell is described in page 8, on page 8, starting in the book. And what we're going to move on is going to be, see what's the, so let me just say a few things that I already last time mentioned about. I will I will mention about it here. So relaxation time, what this relaxation time that Maxwell talked about, of course, keep in mind, it says nothing about molecules, okay? This construct. And our polymer, that even the 100 billion pounds of polymer we're dealing with, molecular weight is important, as I mentioned. To understand processing, to understand rheology, is about to understand its molecular origin. So what is a molecular perspective or molecular expression? Better yet, just simply for tau. Okay, and this is not a trivial question. It was not answered until 1970s. Even though last time I told you that when the chains are sufficiently long, your tau actually is proportional to molecular weight to the third 3.4 power. So is viscosity. So this is something that was known for a long time, but it was difficult to explain why this could be. It was simply not straightforward to explain why this could be. Until a couple of pioneer giant really realized that maybe the way, let's take a we call test chain. They are all chain the same. Let's take that chain here, and the rest of chain, its effect. If there's a way to denote it, maybe that effect is like making sure this chain cannot cross. I said cross several times before already. Chains do not cross. Question? Yeah. So basically, the chain is very long. I don't want to destroy what I have here. Basically, you can see when the chains are mingled together, this chain just cannot cross. Different parts cannot cross. And so, what do I mean? Why do I mention this? Which means when this chain moves around, it respects the fact it cannot cross other chains. And the consequence of that uncrossability is that this black chain, which is the same as every other chain, you just pick up one. That's the concept of the physicist's trait called mean field. Take any chain, which is the same as any other chain. If you can understand the property of this chain, then you claim you understand the chains of all chains, right? Because they are the same chain. They are just a typical chain. What other chains is doing appear to be providing you a tube. Okay? I know I initially draw two-dimensional, but it's really like a three-dimensional. So it's like there's a tube confinement. And this black chain can only swim in this tube, if you like. It's an elegant idea. It simplifies the matter. But keep in mind, you should keep in your mind that this tube is only fictitious, okay? This tube is It's not real. It's just imaginary. But it's just like a Maxwell model. It's a construct. It's a way to help us simplify our story. So it turns out if chain is long enough, then the chains are confined in a tube. And you immediately realize something. You see, if this chain, before that, I can even introduce you. So if there is a tube, you are obliged to introduce its features. For example, the diameter of the tube. If there is a tube you wish to consider, you better say how big that tube is. Well, let's call it A. Moreover, you can even talk about how long is that tube. Let's call it L. Okay? And then you can see that this difficulty of this chain not able to escape the tube. This difficulty disappears if L is as short as A, right? Because there's not a long pipe anymore. So this concept is very essential, okay? When the chains are very short, your tube necessarily will be also getting shorter, so short that the length is the same as the tube, then there is no confinement. It will go out freely. So that concept turns out to be essential. Other than, so in that limit, we basically say that your chain, you are reaching a minimum molecular weight. So remember, I say all this because the molecular weight is sufficiently high, higher than some minimum we call ME. And we will soon define what is ME. As you can see here, you will see here. It turns out if we better relate this abstract L with what we know. What we know for you, most of you guys, probably even Dong should know a little bit. A Gaussian chain is a coil whose size we typically call radius of gyration. Radius of gyration. We know that this typically goes as a square root of how many segments are there. Okay, you treat. I'm not going into all the details, but basically a chain you can think of as made of many so-called cone lengths. So I think this is just a way to think about how flexible the chain is. So the chain is flexible. The chain is not perfectly flexible at the repeated unit. So it turns out that the chain size, if you like to think about end-to-end distance, is not as small as repeated units. That's the repeated unit, L. And there are n of them. So there are n of them from 1 to n. And the chain size, which is usually represented as end-to-end distance, R. And since it's a vector, it's meaningless, so we use the square of the vector so that it has a magnitude. And that magnitude typically is larger than the treatment, than the visualization where the segments are at repeated unit totally flexible. If it's totally flexible, the end-to-end distance would be of this value in the denominator. But it turns out it's always larger than that, so that's why we like to call this so-called characteristic ratio larger than 1. And the other picture of the chain is to treat this as an effective chain, so that as having a unit beyond which is fully flexible. So we like to treat them fully flexible now. And that length is called a cone length. We call it LK. So in that unit, this end-to-end distance will be just NLK squared. So I know for those who haven't seen this, I mean, in fact, all the polymer people should have seen it. This is a mouthful, but it's really as simple as recognizing that the cone length is a larger length scale that effectively beyond that, you can treat your chain as flexible. Being flexible means the end-to-end distance is just exactly linearly proportional to the number of cone segments, okay? So I know I made a little diversion here, but basically now I'm recognizing that the Gaussian chain has the property that its size squared is linearly proportional to chain length. Yeah, because the longer the chain, the more of this cone length there will be. Yeah, so we recognize that this tube should be longer if the chain is longer. Okay, so we recognize that this tube should have a length proportional to n. Well, we know r squared is proportional to n. I know I made a little switch again. End-to-end distance is r. Rg is the radius of gyration, which is related to r by a square root of 6. So I'm going to interchangeably go from r to rg, but accurately, meaning when I say r, it's r. When I say rg, it's rg. Numerically different by this much. So L should be proportional to r because L should be proportional to n. And you can see that this equation is not complete because you have r squared on the right, and you only have one length scale on the right, on the left. So it turns out that missing length is the tube diameter. Or this is your definition of the tube diameter. You get the argument, right? Because we have length squares on both sides. We better have length square on both sides. Okay? And now you can already understand what I mean by when L approaches A. And that is to say your R approaches a minimum length we call it entanglement length. In other words, as you reduce your molecular weight, you are going to reach a point where A squared is the meaning of the end-to-end distance of minimum length. At that level, your tube length is the same as tube diameter. So I'm inviting you to think that you have the freedom to allow yourself to think the chain can get shorter and shorter, and eventually, when it's short as reaching a particular molecular weight, you will no longer have entanglement. So with this in mind, it turns out, it is, this part is just background. I'm not going to insist you have a total mastery of what this is. But just to give you a sense of how this entanglement gave rise to a relaxation time that depend on the chain length. So to do that, it really is talking about a chain or any particle, in fact. When it moves around to another place, it takes some time, and that is called diffusion. And I know somebody else is more familiar with, and remember that this is also known as Brownian motion. Because Brown was the guy who first discovered that the pollen particles under microscope is moving randomly around. And it turns out our polymer or many molecules under thermal agitation will move around randomly like that. Since it moves randomly, it really has no direction. So it goes anywhere they want. So that would be one particle. Another particle may go somewhere else. And another particle will go somewhere else. And therefore, you can see that if I just try to describe this in terms of end-to-end distance over whatever time, it's going to point in all directions. This one pointing this way, this one pointing this way, that one pointing that way, so it's not very meaningful. So the way people do it is to think about R squared. In other words, end-to-end distance squared. And since different polymers, different chains are behaving differently, you have to do an ensemble average. But at the end of the day, what you find is that this, how far away it goes, is linear in the time it takes. Okay? So that's diffusion, fundamentally. Again, if you haven't had it before, or properly introduced before, this is definitely one chance I can describe to you. So this is to describe a particle that moves randomly because of diffusion. The next time it ended up being is how far away it ended up being is such that its absolute distance from that initial position squared is linear in time. That's just the discovery of the Brownian motion. Okay? They discovered. And if so, then of course, you can see this is madness. I mean, you got length square on this side and time on the other side, apple and oranges. So whatever is proportional is also not dimensionless. I mean, it absorbs what, it defines what this dimension is. This is known as diffusion constant. And of course, a diffusion constant, it of course has the dimension by definition of distance squares over time. So since there are six ways, up and down, left and right, forward and back, there's a 6 there, actually. Okay. So this made it easy for us to describe, take a, using this idea, you can see that if you want to have something about time, you really are going to look for length squared, and you're going to look for a diffusion constant. Okay? So in our problem, when we had a chain in a tube, as we had here, our length is the tube length. Okay? Our length is the tube length. Our diffusion constant is something that we can speak about. It turns out this diffusion constant, the way we appreciate what its value has to do with a so-called Stokes-Einstein relationship that I'm not going to go into detail. But basically, this diffusion constant is essentially related to the friction of the chain. And this friction is larger if the chain is longer. So it turns out this friction is basically can be characterized in terms of how long the chain is. Again, n is the number of cone lengths in a chain. I don't know why it's doing this. So you will find out since n is L is proportional to n, as I showed you in the previous slide, and D is 1 over n, you'll find out this immediately says tau should be n to the third power. And that's what we all need to have, to know, that, that your dear polymer become very slow in its movement when the molecular weight increases very quickly. Any question on this? Yeah. Right, as I said, it is by definition the unit of length squared divided by time. It's a there's no, yeah, just by definition. What can you do? And it turns out if you check this expression, it also has the right unit. I know I didn't quite say enough about what is 8 zeta. It's called friction coefficient. It has the unit, turns out, according to Stokes. It has the unit of viscosity times I don't want to confuse you here. I can just say it's the cone length, roughly speaking. Except, sorry, I think I should be careful here. Let me just talk about the units. So the unit of friction is the unit of viscosity multiplied the unit of length. Okay. So all these details, you can find them in all I just covered so far. You can find them starting with page 39 to something around it's just 39 to 41 or so. Again, I don't need you to. You just need to have the knowledge that there are a lot of development talking about how relaxation changes with time, with the molecular weight. Yeah. Right. So I can amplify that point. So theoretically, when we initially, when Dejin initially did this is all due to Dejin, who built the concept of the tube model. This tube concept is due to Edwards. Edwards tube concept. So when they initially worked it out, like Dejin worked it out, it was exactly 3. And then it turns out the way he derived this works very well in the limit when the molecular weight is infinitely long. When the molecular weights are shorter, you can have fancy word, you call it finite size effect. But basically the fact that the chains here are less restrictive, if you like. So that translates to having an effectively shorter tube. Therefore, in reality, the time is faster than the theoretical capture, which is a very good point what you're making, which allows you to say the following. So if you plot your viscosity or relaxation time as a function of molecular weight, which is the same as chain length, which is the number of, same as a number of cone lengths. It turns out, just in reality, it turns out there is a critical molecular weight or critical chain length. So I'm only doing a so-called double log plot. So logarithmic on x, logarithmic on y. Therefore, the slope is the exponent. Okay. In logs, in a double log plot, the slope is the exponent. Okay. So it turns out that the viscosity and relaxation time initially all changing with molecular weight linearly. Slope is 1. And then, as Alex mentioned, it turns into 3.4 very strongly, beyond some magic. It's not magic. When the molecular is sufficiently high, it turns 3.4. And the theoretical calculation of 3 would be this red line. I carefully draw it because I draw it to be larger, meaning above the black line. So in reality, indeed, it was not 3, it was 3.4 because of the fact the chains are not infinitely long. And of course, there were a lot of puzzle or confusion about whether the theory really is adequate because you didn't show it was 3. It was not 3.4 as experiments found. But today, I think everyone accepts the basic notion that you capture the basic part. Yeah, there were lots of effort made by making a sample with sufficiently high molecular weight to show that eventually that it approaches the power of 3 instead of 3.4. Yeah, I think that's so today when we treat a problem empirically, indeed, we acknowledge, as I showed you even here, we acknowledge the change in reality with molecular weight 3. And 3.4 is just, or 3 is just, I'm showing 3 is just for you to see that roughly, indeed, this argument gives you a high exponent quite close to the experimental observation. Okay? Yeah. Any questions more? Okay. So we move on. We move on. This part, let's see, is I guess if I verbally describe it to you, it's still much easier for you to go through the book to look at it. So I could, because it's conceptually quite important, so I could just try to do that for you. So this is something we talked about on page 35 called packing model. So I'm starting another review on part of the introduction. God, did I write down packing properly? No. Not pack. Yeah, it is packing, not package. Packing model. So this is one of the last concepts I'm going to talk about. You see, in the book, it again occupied just a page or 2 on the topic. But I think it's much easier to describe this in person than for you to read it. But then, of course, you have all the things written down there. So I want to come back to the point of this concept. So obviously, something happened when molecular weight is high enough, beyond certain magic molecular weight. Different polymers, this number is different. For example, soon I will be able to tabulate for you what this number is. So the tube model itself does not explain. You know, I introduced the concept when the tube is very short. Of course, you don't have confinement anymore, but it doesn't prescribe. It doesn't describe for you exactly how short is that tube diameter for different polymers. So this packing concept is an attempt to answer the question of what is this critical molecular weight. I know there's a little bit of complication here already. Here, correctly, we use the word MC. There is a critical molecular weight beyond which all sudden viscosity changes very fast with molecular weight. I have to indicate that this MC is not the same as when the tube length approaches the tube diameter. There, we tend to think that this is molecular weight changing from M to ME. So from now on, I'm just going to describe to you what is ME. And roughly speaking, in the literature, people can say, oh, MC is about twice of ME. Everything has to do with the following, that this is a standard notion, that your polymer, I think I invoked this concept once before, your polymer is network-like, even without cross-linking, because of uncrossability that I talked about. Because they are tube confined, I just showed you the tau. So they have they cannot freely move around. But you can see when your chain becomes as short as less than twice of this spacing, you don't have a network anymore, right? So if I call this length entanglement length, then obviously your network can form only if your length is at least twice of this, right? Because otherwise you cannot reach each other in this abstract notation. Okay, so that's one way of thinking about. I introduced several ways to you, right? If you like to consider a tube, obviously when the tube is too short, you don't have confinement or entanglement anymore. When you like to think this in this abstract way, chains are reaching out to each other, then again, when the chains is as short as less than twice of the, then how can they, I don't want to do this one. How can they form? Because the next one, they cannot reach each other anymore, right? You see the point? When they are too short. So this packing model was an effort to ask the question of when it is too short. And this has to do with realizing that this chain in its own physical space, there are many other chains. So the physical space, of course, sorry, I say physical space, so-called pervaded volume. Okay, that of course is the 3 point, that's of course is is this a sphere, if you like. It has a volume of this much. And how many other chains can be in there? Well, that turns out is not such a difficult question, because all you need to ask would be, I want to get the notation right, I call this pervaded volume. All you need to know is what is your physical volume of a chain of molecular weight m. And that turns out is just it's just the reciprocal of this number. Remember, this is nothing but the number of moles per unit volume, and each mole has an Avogadro number of molecules, and therefore, this is how many moles per unit volume, and its inverse is just its physical volume. So I'm trying to see, yeah, that's to try to get it to so this expression is equation 3.19. And how many chains can you have in its pervaded volume is simply this pervaded volume divided by its physical volume, right? Because in this volume, each chain occupy a volume of this much, and this is how many chains you can accommodate. Okay? So this is all, as I said, in page 35. And you will find that this is nothing but I wonder if this concept is already introduced or not. But it's not very very essential. Let's say P. I must have introduced it long ago. It's also in this. So let me just introduce that most important concept, one of the most important concepts in polymer physics. So we just said this is a physical volume of a chain, okay? Physical volume, the actual space it occupies. This volume, of course, should be larger if your chain length is longer, right? So second time, I'm invoking the idea that R squared is linear in chain length. Yeah? Okay? Therefore, I recognize that my physical volume should be proportional to R squared. Physical volume. But since on the left is a volume, on the right is R squared, length squared, there's one length missing. Just like we play with that tube model, there's one length missing. And that missing length is called packing length. And notation is P, little p, lowercase p. Okay? So these are, of course, as I said, I guess every one of you is sort of a polymer person, and therefore, presumably, you all had, certainly polymer physics 1, you all had the concept of cone length, okay, which I mentioned several times already. The unit beyond which you are able to claim that unit is totally flexible. Okay, that's the cone length. I mentioned here in detail. So this cone length. Packing length is nearly just as important a concept as cone length. So if you are to learn polymer physics or molecular chains, this is the second critically important parameter. And it's not hardly written in any textbooks, which is really very, very unfortunate. Okay, be my guest. You will appreciate what P is anywhere it appears again. So the number of chains in its pervaded volume, it turns out, is nothing but R over P. I'm omitting the prefactors, right? There will be numerical factors in front, and the numerical factors, I don't even take my time to write it down. It's written down in equation 27. So this says what? Since R is proportional to N, R squared is proportional to N, and therefore R is proportional to N square root. So this says the longer the chain it is, the more chains you will find in your own volume. Not linearly. It's just the Gaussian property. It's being a Gaussian chain. As I quadruple my chain length, I find in my own volume the number of chains doubled. So it obeys the square root of N. So now you can imagine, I start with relatively low molecular weight, relatively short chain. As I start to increase my chain, I find in my own volume there are more chains in my volume in order to have the density of 1, that of water, because we have no solvent. So you can see that as I keep increasing my chain length, in my own space, I see more chains, more clouded. More chains are packing in the same space. And you can imagine this goes without bound. This will become just even more clouded as you increase your molecular weight. The concept of minimum molecular weight for entanglement. I know that I wrote down this, but in literature, this is called entanglement molecular weight, called ME, which is connected to what I said about the tube getting shorter and shorter until the tube is as long as the tube diameter. So that's coming from high molecular weight to low. I'm here telling you from low to high. In between, you meet that point. That is, there will be a point where it is sufficiently clouded. And that's when you start to have entanglement beyond which you should start to think about chains confined in a tube. Get the concept? So as I keep increasing my molecular weight, there will be one point where it seems reasonable to think my black chain is in a tube. That minimum molecular weight has to do with figuring out what is this number. So it turns out by hundreds of examples, all different polymers, there is something magic. It turns out at the onset, I call it onset of entanglement. In other words, as my molecular weights start to increase and approach ME, my N, which is increasing with N chain length, increases start to increase to a value, guess what? It turns out this value is about 6 to 7. In other words, if I have 6 or 7 in my own volume, that's about the place beyond which I start to see other chains interfering with me. And the magic is this number 6 to 7 is the same for all different polymers. That's the most powerful, which you can accept. Who cares it's polystyrene or polyethylene? As long as I see myself being surrounded by 6 chains, you are getting to a point I'm not comfortable anymore. I cannot move much anymore. The only way I can move is through a tube now. So the power is not just this concept, but rather the bold assumption that all polymers, all linear flexible polymers, will start to get equally entangled or start to feel clouded at the same magic number of 6 or 7 universal. Question? Yeah. Right. No, so not surrounded. Q is, you have a pervaded volume, which I defined here, huh? Which is just the size of that Gaussian coil. But that coil is not space filling. It's just right? It's just like this. It's a coil. So it's empty, a lot of empty space. So you need to introduce all other chains in it, the same volume. And Q is ask the question, how many chains are there in your own volume to fill the space? ME is the minimum molecular weight. It turns out as I jumped on, it is when the Q becomes 6 or 7. MC is a way to define when the viscosity start to change from linearly dependent to its critical value. And since we don't talk about MC anymore, I just say it's about twice of ME, roughly. Yeah. Good point. Nobody knows. Oh, no, I saying, meaning it was a good guess that doesn't matter what polymer, there should be a magic number beyond which it feels too clouded. So yeah. Yes, that's what it says. Yes. So don't be confused. Yes. So let me rewrite it. Any chain length it will be this. So at when it is higher than a critical molecular critical chain length, then the number will just grow quadratically. Yeah, in fact, this is I know today, I don't want to go too long today. I know this is a good time please, further questions. But otherwise, this is a perfect time to end today's session, actually. As I said, nearly nowhere you will learn about this concept of packing length, packing model, and packing length in any textbooks. For example, we use a textbook by Rubenstein and Kobe called Polymer Physics. It was omitted but this is actually a very essential part. Let me close by asking you to develop a sense of what is P. It is this chain, its physical volume, not just physical volume. And just watch that equation, right? It is, that physical volume is R squared. So if I kind of try to put my chain collapsed onto a two-dimensional space, okay, it will have an area of R, yeah, and a height of P, yeah, roughly speaking. So it turns out this P has the meaning roughly about the molecular thickness. It's absolutely essential concept. Molecular thickness, how thick this, so it turns out there are tons of literature and including, yeah. So basically what I'm trying to say is, turns out it's tabulated for all polymers. For example, polyethylene will indeed look like this one, very thin, skinny. Polystyrene will look like this one, very thick. And everything in between. And if you hydrogenate polystyrene, it's even thicker. So, and that's just enormously important. In terms, we'll develop a little bit, but in terms of dealing with polymers in general, because polymers mostly stay in this condensed state. Okay, I know there are solutions, but in this condensed state, it's all having to do with how much space is there. And how thin, how thick the samples are very important. And this is all captured in here. So for example, so I will upload the papers. For example, give you a sense. P is about 1.6 for polyethylene. P is nearly about 4 for polystyrene. I didn't give you a unit. What unit? Angstrom. So with that benzene ring, it looks very bulky. And, these two are nearly the limits, and everywhere, anything is everywhere in between. Yeah, so if you have a copolymer, it depends on how often you put some side chain there, and so yeah, it's an average sense, right? Yeah. Okay.